Okay, back again. 5.2 is inverse functions. So I think we'll do this one again in two parts, just so hopefully these videos load faster and I can get them up to you quicker. So inverse functions, what we're looking at now is we've looked at all of the function operations, composition. We've checked to see if function or if a relation is a function. And now the last thing we want to do is look at inverse functions. And the word inverse in math is kind of like the word reverse or to undo. So, excuse me, what we're looking at is we're looking at two functions that are kind of like opposites of each other. And we've got two very common examples of inverse functions. So before we even define anything, let me show you two of our base graphs, and I want you to see how similar they are to each other. Okay, so for our base graphs, let's look at y or f of x equals x cubed. And notice how, remember, x cubed is this squiggly looking guy. And I want you to notice how closely related he looks to the cube root of x. So these guys have similar shape, but just a little bit off kilter of each other. And basically, if you look at the two functions themselves, if I was to ask you what would undo a cube, your answer to me would probably be a cube root. And that's what we're looking at. What's the reverse or the opposite here, or the inverse? And so when we look at the two functions, we can say, yeah, you know what, I think they're related, and the two graphs and the two functions kind of show that as well. So that's one of our most common examples. The other example that we have is with probably our most common base graph all around, and that is the x squared. And so x squared is just our basic parabola, okay, our wonderful, beautiful parabola. And then the other graph we're going to put up here is the square root of x. But the square root of x looks a little bit different. The square root of x looks like that. So over here, these two guys, they have very similar look to them. Basically, it's a reflection and a reflection. So if we were to take this graph and it's a diagonal reflection, let's put it that way. If we were to take this graph and diagonally flip it, we will get this graph here, so a diagonal flip. Okay, so there is a reflection going on here, but this one doesn't have the same reflection. And the reason why is that it should look like that. Now, if it had both parts here, then don't these two guys look very, very similar to each other, okay? So yes, they undo each other, but what happens here? If I were to run a vertical line through here and it contains this green part, do I have a function anymore? And I don't, do I? So when it comes to the square root of x, we're not going to use the negative part, we're just going to use the positive half. Okay, so what that means, or what that should kind of spur in you, is that there are going to be issues with the domain. So domain issues, yay, okay? All right, so why does that one reflect diagonally so well and this one doesn't? Well, there's a difference between these graphs and those graphs, and that's where we're going to start this idea of inverse functions. Okay, so we're ready to actually look at the lecture here. So in order to have an inverse, we need what we call a one-to-one function. So the only functions that have and inverse are one-to-one functions. So what does that mean? And what that means, so a one-to-one function, or sorry, let's say it this, in a one-to-one function, each x has one and only one y coordinate, and each y has one and only one x coordinate. All right, so to be one-to-one means that you've got to be a function both forwards and backwards. So remember, in a function we said that every x value has one y coordinate. Okay, if you've got an x, if x is 1, it only goes to one place. But now, in order to be one-to-one, that needs to work going backwards as well. So every y coordinate has one and only one x coordinate. And that's where it gets the name one-to-one, because it's one and only one. So every x is attached to just one y, and they go together. As soon as you know the x, you know the y. As soon as you know the y, you know the x. Okay? So there are two ways that we check that. And the first way or the easier of the two ways, is the graphical method. So, you know what, I can draw this again. So to test to see if a graph is a function, if you remember, we used the vertical line test. To test to see if a graph is one-to-one, we're going to flip that around opposite and do the horizontal line test. So the horizontal line test this says, if no horizontal line crosses the graph of a function more than once, the function is one-to-one and has an inverse. So basically same idea, written in the negative, so if no horizontal line, but basically we can cross the graph 0 or 1 times. So 0 or 1 cross is okay. So as we looked at our base graph there of x cubed, if we take any horizontal line, that's going to cross the graph only one time. Any horizontal line only crosses one time. So we are good. I mean, we could run them through anywhere. We're good to go. So that's why our first example there worked so nicely. But if we have that other example, so if y equals x squared, so we've got our parabola there. What happens when you go with a horizontal line here? So if I take this horizontal line right here, that crosses the graph twice, doesn't it? And since that's the case, this graph, this function is not one-to-one. So this function doesn't have an inverse. So not one-to-one. So there's no inverse. But we know that the square root undoes the square. We know that, we all know that. So how is it that this isn't working? So this is a one with a domain issue. And because this is, our most useful graph, it's one that we see often in real life scenarios, this guy has to work, okay? And we know that it actually does have an inverse. So the problem here though has to deal with the domain. So what we're gonna do, and you don't just normally do this, this is something that was done with this function to make it work because we need it to work. So we're going to restrict the domain. And what I mean is, not me personally, but mathematicians as a whole decided, let's do this, okay? Let's look at a domain from 0 to infinity, okay? So what they're saying is, let's only look at the positive side. So they're saying, let's just go whoop and get rid of this whole side of the graph. So now we're looking at the graph of the positive half of the parabola. But here's the dealio. The parabola is symmetrical, isn't it? So if you know what the positive half of the parabola looks like, can you mentally know what the other half looks like, what the negative half looks like? So even though it should have this other half, because of the symmetry, we don't actually need to see it. And if we restrict the domain and look at this, now have we created a one-to-one function? And we have. Okay, so now it's one-to-one. And that works for us. Okay, that's what we want to see. Now, another way to do this is to do this graphically. So let's say that you don't know what the graph looks like, you don't have your calculator with you, so you can't test one-to-one by looking at a graph. So we have an algebraic way of doing this as well. So we say, given, and how do we want to say this? Unfortunately, I just have the actual formula written down, but I don't have the words that go with it, so I'm trying to think. So let's say two functions, not two functions, a function is one-to-one if f of A set equal to f of B leads to A equal to B. So a function is one-to-one if we plug in if we plug in A into the function and B into the other function and set them equal to each other, and that leads to A equaling B, then we know that our function is one-to-one. So I know it doesn't come out quite right, but this is what we're basically doing. So let's say that our function was f of x equals x cubed minus 4. Okay, just to give us something there. So what we're going to do is we're going to find f of A and set it equal to f of B. So basically we're just going to plug A into there and then we're going to plug B into there. So we're going to have A cubed minus 4 equals B cubed minus 4. And then what we're going to do is we're going to undo this or simplify this or solve it. And the hope is that in the end we end up with A equals B. So this is how this is going to work. So if we add 4 to both sides, do the 4's go away? Yes. So we have A cubed equals B cubed. And now can we take the cube root of both sides? Sure. So take the cube root of both sides, and now we end up with A equals B. So we started out with f of A equals f of B, and ding, 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 we end up with A equals B in the long run. Okay, so let's look at one that doesn't work so that you can see what it looks like when it doesn't work. And let's say that we had f of x is equal to negative x minus 5 squared. Okay. So we're going to set f of A equal to f of B. So we're going to plug in A and plug in B. So we have negative A minus 5 squared equals negative B minus 5 squared. Okay. And again, the idea is to try to eliminate values and stuff. So if we've got a negative on both sides, aren't they going to cancel each other out? Okay. So we really don't need the negatives on both sides, so that cancels out. B minus 5 cancels out. Okay. Now, can we take the square root and eliminate the squared here? And we certainly can, but there's an issue. When we take the square root on one side or the other, when we take the square root of a problem, we have to put a plus or minus sign. So we'll do a plus or minus, parenthesis, B minus 5. It's not just A minus 5 equals B minus 5. We end up with this plus or minus sign. So you see how this is kind of leading us to something that's not really going to be great. So we now have two equations. We have A minus 5 equals B minus 5, or A minus 5 equals negative B minus 5. Now, in this one, can we just get to A equals B? And that looks good. But there's this word or. Down here, we've got A minus 5 equals negative B plus 5. So are the 5's going to cancel out? It's like if we add 5 here and add 5 here, we get A equals negative B plus 10. So do you see any way on this one that we're going to end up with A equals B? It worked for one, but if you've got that or, it's got to work for both of them, and this one fails. This is a big... So this function is not one-to-one. Okay, it's not one-to-one. And normally, if it is one-to-one, this will flow very easily. You just plug it in and everything cancels out, and you're done. And you're kind of like, why the heck did I just waste my time doing that? So these are the ones that work nice. This is the one, as it starts to get uglier and uglier, you can kind of go, oh yeah, I'm seeing this isn't going to work out. Okay, so that's the first part of the lecture, is discovering when we have an inverse, so the one-to-one, so making sure that we actually can do an inverse. Then the second part of the lecture will be the actual finding of the inverse, okay? Holy cow, that one was 18 minutes. Long.